Hi everyone, my name is Daria and welcome to MOE 101 Guide series. Today we are going to focus on implementing an actual MOE model from scratch. Yes, you've heard it right, an actual MOE model. There is a common myth that mixture of experts are only accessible for big tech companies because they can afford to train them. But this is just not true. And today we're going to bust this myth. By the end of this guide, you will be able to implement an actual MOE model with just a few lines of code, train it, and see how it beats a dense baseline. To beat the dense baseline, we're going to specifically focus on the learned routing mechanism that we introduced in part 2 of the MOE 101 guide series. That learned routing is the industry standard and is being used across all of these great MOE models released out there. As for the expectation, we are going to train a very small MOE model with just 4 experts and 1 active, and we are going to expect something on par with 2% improvement against our dense baseline. As for the dense baseline, we are going to take GPT-2 style network from modded NanoGPT codebase. This is basically a modernized GPT-2 that has rotary embeddings, muon optimizer, squared ReLU nonlinearity, etc. We are going to train it on a fine web dataset, and specifically, we're going to take a portion of it, which is very tiny as well, just 2.4 billion tokens, which is about 20 tokens per active parameter. Cool, so let's actually implement everything. Download the modded NanoGPT MOE codebase. I already did that, but feel free to do that on the background and then come back to this video. We're going to specifically work on train.gpt moe.py file that we already pre-cooked for you with all the necessary layers. Feel free to code along, or you can just listen to me and understand what different parts of MOE models are doing. The first thing we're going to work on is called the expert network. As you guys remember, we have different types of layers in a transformer, in the decoder block of the transformer. We start with the embedding layer, then we have attention layer, and we finish off with an FFN block. That FFN block here is called MLP. Each expert now is going to be a separate MLP block that doesn't have any different architecture. It's going to be just the same MLP copy-pasted. So you can see that each MLP essentially consists of 2 different linear transformations. One is called up projection, so it's this one. Another one is called down projection. And in between of them, we have a squared ReLU nonlinearity. Now, each expert will have its own MLP block created. Let me show you how. So here, we actually instantiate MLP layers and create them separately for separate experts. This will allow us to actually train different experts with different weights and sort of hope that each expert will specialize in something, specialize its own weights. Cool. So now we have experts created, and each expert has a design which is the same as GPT-2 FFN block. How are we going to use these experts? There is a special function that we created called expert mixing. In that expert mixing, there is a logic on how to use those experts. So let's imagine that we have a token and some router already implemented the logic for us that tell us which token should go to which expert. So the result of that router work is actually stored inside expert IDs. So expert IDs are those experts that we selected for a given token. Now is the time to actually move the relevant tokens through the experts that were selected for them and perform the transformations. So you can see that this logic is implemented here. Let's say for top key 1 expert, we're just going to select 1 active expert for a given token, the best one, and we're going to get the output from that expert multiplied by the probability with which it was selected. You can see that this implementation is not really fast because it has to loop through all the experts available in the network, and it's not really efficient. We're going to use it just for demonstration purposes. Okay, nice. So we have expert mixing set, we have different experts created. Now is the time to create a router. We already created this class called Learned Router for you, and it basically has two purposes, right? The first one is to find the best expert suited for a given token. And this is the logic that happens exactly in this forward pass, right? So we have the linear layer and we have a softmax and the linearity on top to create the probability space for different tokens and select the best top K probabilities, normalize them, and return the output. In addition to that, learned routing has to load balance. There is an additional auxiliary loss that we add to the cross entropy that basically controls how well are we utilizing the full capacity of the network, all of the experts that are created. So you can see here the implementation for auxiliary loss as well. We basically count how many tokens experts were actually received versus how many we expected, and we penalize for misalignment. Okay, cool. So we already have the learned routing implemented and all the other components necessary for MOE. So now it's a good time to kick off our first training run. The first thing to check before you do that is how many experts you specify. So I set 4 in my setup. Top key 1, so we just have one active expert selected for a given token. The other thing that we want to check for is called auxiliary loss coefficient, and we set it somewhere here. Yes. So we set it to 0.01, which is the standard value. We haven't tuned it for this setup, but feel free to play with it. You can either improve the quality, maybe going smaller, but also check how much load balancing you're having by, let's say, setting auxiliary coefficient to 0. Now, feel free to go to our repo and find the exact command to type into your terminal given your setup. I'm going to be focusing specifically at the results that we are getting after the first run. So here, how your MOE curve will look like after you kick off training. I also conveniently launched dense GPT-2 model as well, so we can compare against it. Feel free to compare to my curve or relaunch your own baseline. What we are seeing here is quite early in training, MOE model is outperforming dense, which is great. And towards the end of training to 2.4 billion tokens, we are actually about 1% ahead compared to dense GPT-2, which is a lot. Think about it this way. You haven't increased the flop budget. You are training it for the same number of flops as the dense baseline, but you are improving the quality by 1%. Which is a lot. But you might wonder, in the beginning of this video, I actually said that we have 2% improvement as a target. However, we are not getting that. The question is why? Usually this is the place that gets really frustrating for most of the researchers when there is this shiny paper with a shiny new router created and shared. You try to implement it and it just doesn't work. Well, this is the exact place where we are right now, and we're going to fix it. We're going to debug together what's going on with our routing method, fix the problem, and actually hit our 2%. Since we know that our router has 2 different objectives, one is load balancing. We want experts to be utilized. We want to utilize the full capacity of the network. And the first thing to check is whether we're actually learning that. We already added all the useful metrics for you guys to look at, so you don't have to implement it from scratch. You can just visualize that. After you visualize expert utilization, you will see something similar to this. So this expert utilization is averaged across all layers, but you can look at one particular layer to see how different it is from others. What's important here is we see that we have 4 experts created, and towards the end of the training, we have something about 25% of each expert utilized, which is perfect. So the load balancing part of the objective for the router is working great. Yes, you might see some noisiness in the beginning, but this is normal. In the beginning, the router sort of still hasn't learned that there is the load balancing loss objective, cross entropy loss objective, how much gradient comes from each of them. So it's okay to expect something like this in the beginning of the training. Okay, so since we are load balancing pretty great, what can be going on with the router? Why it is not getting this 2%, basically getting half of the expected improvement? Well, the easiest way to analyze that is when you have a dual objective set for any neural network, is to look at the amount of gradient that comes from each part of that objective and understand whether you're optimizing them or not. We know that we're optimizing load balancing, but let's look at the gradient norm that comes from the cross entropy as well. Here I have the gradient norm that's taken from the middle layer of the decoder block, and we plot how much the gradient norm is changing throughout the training course for two different parts. One part is the cross entropy part, how much gradient norm is coming into the router from cross entropy loss, and the other part is how much gradient is coming into the router from the load balancing. You can see that load balancing is pretty great. We have a lot of gradient coming, hence we have a perfect utilization. However, the amount of gradient that comes from cross entropy is really minimum. You can see that compared to load balancing is just zero. What it means is that your router is only getting useful signal from the load balancing part of the objective, and it doesn't learn this token to expert alignment that we instructed it to learn. The best way to understand where the problem is happening is usually to try and isolate it. So if you're looking at our learned router class, we see that there is this place where we call the top key for different top key values. Doesn't matter top key 1 or top key 2. And we perform this additional normalization that is required so the final set of probabilities, this final set of values still forms a probability distribution. Now, let's look at how top K2 amount of gradient looks like. Here I plotted exactly the same thing, the gradient norm that comes into the router from cross entropy for the top K2 scenario. We can see that we have a completely different picture. In this picture, there is a sufficient amount of gradient that comes into the router, and it's actually increasing towards the end of our training, which suggests that something is specifically wrong with our top key 1 case, right? You see that there is a flat curve with almost zero values for the router grad norms. Let's take a closer look. So if we actually look at this step, with the top key 1 scenario, your gate that basically gets initialized here just has one value. And when you perform summation across all of the different top key values, it's just summation across itself. And when you divide the gate network by the gate network itself, you basically always get values close to 1, right? So there is precision loss, but the value, if you round it, is going to be a 1, probability of 1. What it means is that this is the place where your router is halting the learning signal. How is the top key 2 situation different? So in top key 2, you don't have this problem, right? Because you have always 2 probabilities in the summation, and hence you won't be normalizing the probability of the top 1 by itself. In addition to that, this part of the code allows the router with a top key more than 1 scenario to sort of have a contrastive logic designed in it. What I mean by that is, imagine if I'm asking you whether you're interested in math, and you're giving me 0.5 probability of yes. That doesn't give me anything, but what if I actually ask it this way, whether you're interested in, tell me if you're interested in math or in physics, and you're giving me 0.9 probability that it's math, I'm more interested in that. That gives me way more signal. So let's actually implement the same logic for top key 1 case. What we're gonna do, we're gonna add a phantom expert, sort of an expert that never gets activated, but is silently present there for the router to contrast against. Here is how we're gonna do that. Let's call it null expert bias. Then here we're gonna create the variable for the class, and we're gonna add it here. So now you can see that this expert is always present to contrast against, hence it's in denominator, but we are never activating that. Hence we are not adding it in this part. This trick is actually inspired by the work called ReZero that was published a long time ago, and essentially their authors were trying to enhance amount of gradient signal that comes into the deeper layers of the network to improve the quality. Well, we are doing the same thing here. We're trying to elevate the amount of gradient that comes into the router network with the top key 1 case. Now, null expert bias can be set to different values. This is essentially a tunable parameter, and you can always make it learnable. In our case, we didn't spend much time tuning it, and we just set it to something close to 10, but you feel free to experiment with it and see how much gradient boost it gives to the router. Now, let's time to kick off another experiment with a null expert bias set and check out our gradient norms. I already have them plotted here, so you can see that here I'm comparing the top key 1 case for 2 different implementations. Our previous one, the blue one, remember that flat curve with 0 gradient coming into the router from cross entropy, and now with the null expert bias trick. You can see that we elevated the amount of gradient that comes into the router by a lot. From almost 0 value, you're already getting the non-trivial amount of gradient, which is amazing. So now the question is whether that improves the quality of the model. So what we are seeing on this picture is we're still having our dense GPT-2 model plotted, our previous result with 4 experts against it that was giving us about 1% improvement on top, but we wanted more. And here is our blue curve with a null expert bias that allowed us to reach that 2% improvement for the same compute as we originally promised. So now let me recap what actually happened. We started with a goal to train 4 experts model and beat our dense model by 2%. The first run, it went well. We got 1% improvement. We were good at load balancing, but we already hypothesized that something might be wrong there because the improvement is only half of what we expected. What we did after that, we root caused the particular issue in our router, added a targeted fix, and boom, you now have what you wanted. You have an MOE model trained with this tiny number of experts for no increase in the computer budget compared to dense models, so top key 1, and you're beating it with a 2%. And notice that we didn't have to spend time tuning hyperparameters or perform those batch size sweeps or increase the number of active parameters. So now you know for yourself that MOE models are tricky, but they are real once you make them right. Thanks again for watching this video. I hope you enjoyed it, and see you in the next editions of MOE 101 Guide.